Good morning. Time to get after this. There it is. Today, we're going to talk about strings and sequences. Pull up my slide deck here. We've got some pretty interesting illustrations here. On the far side, we can see a representation of DNA, which we'll talk about how that has a string relationship. Obviously, the DNA is a sequence, so that fits in there. Up here, we've got an illustration of a sliding window search. We'll be looking into that as well. Down here, this is just a violin. It has strings. And then there's something over there with strangely focusing, but not really magnifying glass. But I digress. Let's get after it. Why should we even bother studying string algorithms? That's our first big question here. The bird's eye view, of course, is that strings are just character sequences, and sequences are very important across most of the work that we have. The sequence of operations, a sequence of data, all manner of sequences are important. So strings are just a particular type of sequence. We think of them as having some set of characters which are taken from an alphabet, and that alphabet is kind of like the universal set when we're talking about items. All of the possible characters that are available, and then our strings are made up from some subset, some items chosen from that alphabet. Then we've got all these algorithms on strings that are really just array algorithms. They're things that deal with sequences. What makes these arrays sequences special is just because there's a lot of typical tasks. We'll look at some of those. We'll look at some typical applications that are very commonly done with strings that are arrays of characters. Actually, when I started programming, this is pre-C++, in programming in C, as I should say. When I started programming in C, we just had the char type. And you can see now that C++ still only has the built-in char type. We do have the string object from the STL, but that's an add-on to the language. It's not part of the core language. The only thing that's part of the core language in terms of built-in types is the character. And so we still referred to them as strings, even though there wasn't a string thing. We talked about a string as being a collection of characters that are all strung together. This was generally either a character pointer or a character array, but that was how we dealt with strings. We've got a nice wrapper class from the STL around that now, but at its heart, it's still just a bunch of characters all strung together. We've got some applications of interest we'll be poking at when we're dealing with human readable text. So not all of our strings that we're managing are human readable, so that's important to point out. So some of the things that we are talking about will be here. We'll talk about some common character sets, the ones that we still use most of the time today: ASCII, Unicode, UTF-8. Names and labels, of course, things like people and files, license plates, those are all things that we need to manage in our daily lives. DNA analysis, as alluded to on our front slide there. It's just very interesting as we figure out what's going on with DNA, as it's this collection of sequences. It's just a great big string analysis. What's out of scope, of course, that we're not going to be dealing with is sequences of objects or doubles or things like that. When we're working with strings and sequences, we've got some questions that we often ask. Given two of them, how can I tell if they're equal? Which one would I say goes first in a dictionary? That's more like a less than or equal. What do we have in common if I've got two strings? Are there substrings that they share? Is one string completely subsumed in the other one? How do we find the differences in two strings that are similar, or how similar they are, or how different they are? Another task that we have when working with strings and sequences is, given many of them, put them in lexicographic order. That's dictionary order, and it's got to be easily the least fun word to say this entire semester. Lexicographic, lexicographic, lexicographic. You try it. Go for it. So that is dictionary order, and I'll probably say it once or twice more this lecture, but then I'm going to try to shorten it up. So obviously, we have a lot of algorithms that predicate our data being sorted. So if I've got some sort order for strings, it might help with a lot of things, like searches and things like that. So as we work with strings and texts now, let's say I'm looking for a word or some phrase in a large body of text. This has often been sort of given the phrase searching for a needle in a haystack. And we're going to do that with this particular example. So given two strings, P and S, that P is the thing that we're looking for, and S is the thing that we're looking in. For instance, we might say, find all the instances of P in S, or maybe just the first instance, or maybe the last instance of P and S, or maybe I want to go through some method that allows me to step from one instance to the next, to the next, the next, the next. Or I've got other applications. Have you ever worked with an editor that has a refactoring tool? Find all of the versions of this string and change it to another string. One way that we can do this find is just to grind through this one at a time. Another way to do it is to pre-process S before P is known. So if I can pre-process, if I got some string that I'm going to be searching on a regular basis, before I know what the search term is going to be, I could pre-process S and then optimize my searches so I can have a lot of independent queries for different P that can give me really fast results. So we talked about characters and how we put them together to make strings, but this new term up here at the top, what is a text? This definition down here at the bottom says a text is a string. Of course, this is a string of letters, but now we're going to be using separator characters. Some particular character that is not like the other characters. It's a non-content character. It's a position retaining or creating character. It's a space. That's the most common one, but we have other separators. We think of the C++ language as using the semicolon. We call some of these languages curly brace languages or semicolon languages. Those are both separators that are used to divide our tokens into the things that we care about and just moving on to the next thing that we care about. So one of the things that we're doing here is given some word or even a phrase, find the instances of that in a text. So a text is a much larger thing. To be clear, a text is generally still a string. Sometimes it's a collection of strings, but it's a string that has separators, so we can think of it as not being a single token. And that's another word that's used in strings and dealing with characters like that is the word token. So I can take some long text and break it up into tokens. That means taking the string and using the separator to make it into a bunch of smaller strings that do not include separators. It's tokenizing. A text corpus is what I mentioned earlier, is that we might say that a text is a really long string or sometimes multiple strings. But as we talk about these multiple large strings, another way to look at this is something called a text corpus, which is now a collection of these documents or texts. Each one has a text, which is something that has the string in it, as well as some metadata, other attributes, URL, author, copyright, citations, and the like. So when working with a text corpus, you might say, well, given some search string consisting of one or more words, find all the documents, right? A document is a bunch of texts, a collection of very long strings, maybe not so very long, but they're a collection of independent strings, each with their own focus. Each one has its own title or things like that. So one thing you might do is say, given some search string, how do I find all the documents that contain those words? Maybe I sometimes want an exact match because I'm only looking for this exact pattern. sometimes approximate matches might be warranted. I might say, maybe I'm looking for Mike, but I would settle for a Michael as well. And another thing that I might do is I might say, I don't exactly remember how to spell receive. Is it I before E except after C, or is it RECEIVE or RECIEVE? I don't know. I'm looking for that though. And one of the things that might be nice is if you figured out what I wanted, even though I wasn't quite able to articulate what I wanted. And there's a very, very large industry built on this, one of the largest companies on the planet here. It's over there. One other thing that we might do is say, let's take all of the Project 1 submissions and find pairs of similar programs. Now, that wouldn't be yours. Yours wouldn't be similar to anyone's, would it? No. It's honor code and things like that. But we've got to check, you know, that's our job. We got to be diligent there. So that's an example of how you take a text corpus and pull information out of this collection of data. How about text compression? That's a good one. As we save space, text is one of the easiest things that we have to compress. We've got a lot of data that we mess with now, but text is one of the easiest ones to compress. Still, we get a lot of savings normally when we compress our English texts. One of the ways we do this is we find repeated words, like the word the, for instance, and say, well, that's the word we're going to see the most. Maybe we'll just represent that with some number, but it's important that this number is small enough to actually achieve compression. That's kind of the tricky part, right? So think of THE as 3 individual bytes. So if I've got some number that's longer than 3 bytes, why not just use the word? So that's an interesting approach there. Text compression is not one of the things that we cover in the course, but it's worth noting that you could go and track down some of these algorithms, even at a high level. When I say high level, I mean even at a Wikipedia level. Go look at a page, go see how tarballs work. What do we call them? Tarballs. Tar, TAR, which stands for tape archive, which was a command that was used to take a bunch of files and or directories and turn that into a single file. So then you could take that one file and compress it. That's what the compression aspect of it is. So the tarball is when you take a tape archived thing and then ball it up as small as you can and pass it around. Normally we look at those as TGZ files or tar.gz files. So that's one of the things, a little bit of background there. All right, slide, come back. DNA and genomic sequences. Here's this picture from the front slide again. We see this double helix that represents the way that the DNA structure looks when we take a close look at it. It turns out that our DNA structure is defined by the different sequences of these nucleotide base pairs. And these base pairs are fairly simple in the way that they are pulled together. It's just the multiple combinations and the sequences of them. So if we were to represent DNA with letters, it's fairly easy because it's got a small alphabet. It really only has these base pairs that come up with one side of the pair as an A, a C, a G, or a T. I'm not quite sure why they named them that. I'm sure there's got to be some really good chemical reason. But every one of these genes is really just a combination of pairs. So I got a couple of A, C's, followed by some GTs or something like that in this position. And that's how our bodies know to grow hair on the top of our head instead of on the front of our face. I don't know. I'm not that deep into it. Dr. P has got mad knowledge on this stuff, so you can talk to him about it. He's done quite a bit of this stuff. So check that out. And people, we have these 23 times 2, these 23 chromosome sets, which ends up giving us some 3 billion base pairs. And if you can represent all those as characters, you can say, if I'm trying to figure out what a particular gene is, a gene is just a subsequence, some collection of these pairs in a row. And as you identify, well, this gene causes people to grow tall, and this gene gives people a resistance to the common cold, or this gene gives people longevity. All of that work is running through this gigantic 3 billion base pair data set and comparing one of these to another. So how are these two people similar? This person has a debilitating disease and this person is not affected by it. Where do those distinctions come from? As we look this up, is this something that just happened to the person, or is it something that is genetic? So we can use string algorithms to compare chromosomes, to look up genes, and then we can use them also to sort of assemble these long DNA strands from short sequences. You could even revive dinosaurs if you wanted to put some stuff from an old piece of amber along with some frog stuff, and who knows, right? That's Jurassic Park. But it is, at its heart, one of the things that is really going to be pushing our science for many years to come as we learn more about ourselves and the world around us. So being able to work inside that string area is vital. Looking at these data structures, I talked already about when I started programming in C, and we just had these characters in a row, and you had some way to get to the beginning, whether it was a square brackets array notation, or if you were feeling kind of froggy, you could say, give me a character pointer, and then I'll go reserve some memory there myself. We always had to reserve one more byte than we planned on having for our string. So if I was going to use my name, Darden, I had 6 characters, I would need 7 bytes because we were always going to null terminate that. We had our pointer that pointed to the beginning of the data, then we had the amount of bytes that we needed for the data itself, and then we had one additional character, which is the null terminator, which is really just another character, which is just 8 bits of pure 0. 8 zeros in a row, that was our null terminator. And all of our string operations, our old school C, our C string operations, for instance, something here like measuring the size of a string, all you would do is send it to the beginning of that pointer, and then the algorithms were written in such a way that they just continued and continued and continued until they saw that null terminator, that null byte, that full-on 0. That's when they would stop. So they didn't have us say, well, I want you to process this string, but in order for you to process the string, I have to tell you how long it is. We didn't have to tell you how long it was. We said just go and do a string copy until you hit a null terminator, or do a string compare until you hit null terminators. And that's how that worked. When we worked in C, we were always in ASCII. That was what we had. We had these pointer arithmetics and standard lib from C functions. We got into C++, now we're object-oriented. Now we've got these objects that are quite a bit more complex, and they've been made even more complex just recently. So C++ 11 style, or was it C++ 14? Somewhere right in there, they jumped up in complexity, but that complexity was deemed worthwhile for the speed that it involved. So now when we think of a C++ string object, we can think of that as at least 2 pointers. We got to have a pointer to the beginning and a pointer to the end of where that memory is. We may have an additional pointer if things get off into the heap there, something. But our current C++, at least in the GCC version of this, the way that the standard library STL uses strings, is this 32-byte object for a string. No matter how long the string is, it's going to be 32 bytes used for the string. And when we've got a short string, something less than 16 characters, I think it's on the order of 15 bytes, so it depends on what your alphabet is going to be used. So you've got 15 bytes of those 32 bytes that can actually store string data. And if you've got a short string that can fit in those 15 bytes, then the 32 bytes that is the string holds all the information. If you've got a longer string, then one that's longer than 15 characters that won't fit inside of the 32-byte object, then you still have the 32-byte object, but when you dereference the pointer inside of the 32-byte object to get to where the data is, it will have been already allocated and stored elsewhere on the heap. So the string object itself always works the same way. There's a pointer in the string object that points to the string data. When it's small enough, the string pointer points inside the current object. When it's too large, the string pointer points outside onto some dynamic memory allocated and maintained on the heap. When we're using these C++ strings, we've now got the ability to change the alphabet that we use. We can configure that. When I've got the two pointers, begin and end, instead of having to count from begin to end to figure out how many characters are there, I could subtract begin from end in a constant amount of time and check the size of an object. That's just an example here. We've got a bunch of methods and operators that come along with our new C++ style things. There's a standard lib C++ functions, the STL, and they also give you access to the C string, or just the character pointer data as well. So you could use these C++ string objects with our old version of the C style functions and still get good answers out of that. When we're dealing with these sequences, remember that a C++ string is a sequence, and the STL loves sequences. The STL loves to deal with ranges. It's how it deals with things. These iterator ranges. So our C++ strings, which are really sequences, really can also be covered by an iterator range. So you can call begin and end on them and get something that you can then use like any other iterator sort of thing, where you can plus and dereference and compare depending on which particular type you're reading with, or write, and all of those things. So we've got some specialized containers for multiple strings. For instance, dictionaries, which allow us to add and remove and look up words. We've seen the dictionary in the unordered map. We've seen it in the not so unordered map, which is just the map. We've got strings that have shared fragments. For instance, many words start with anti or pre or over or semi, things like that. So we can start to use specialized containers that can optimize the use of words like this. How do we check for equality in the STL? There's a standard equal, and standard equal is just for sequence equality, any sequence. So you can use standard equal to compare items in a vector. You can compare items in a deck. You can compare items in a deck, two items in a vector, or anything that really is going to allow you to do something that looks like an iterator. So I can grab an iterator into a string, so I can use sequence equality here with standard equal on strings. And so it's important to read how this function works here, right? I've got 3 parameters to equal. That's important to understand. I've got the input that I'm checking here, and that goes from first one to last one. And then what I'm comparing it to, which is the data that starts at first 2. You'll notice there's no last 2. I don't need to know where that second sequence ends. If I'm going to be checking these things for equality, it's kind of up to me to make sure that they're the same length. That's the most easy thing I can do. Most sequences that I have in the STL, I can check their length in constant time. So as I'm looking at this equal function that is going to be comparing things one at a time, linear at best, why wouldn't I just check beforehand to see if one was longer than the other? If one was longer than the other, I know right away they're not equal, because this Boolean equal function just says, are they equal or not? If they're not the same length, they're not equal. So this function is assuming that you're going to send it 2 things that are equal. Now, if you send something that is, the first one is longer than the second one, you've got a really good chance of reading off of your memory segment, because that's not a great thing. If you send something where the second one is longer than the first one, there you can find a prefix. So the word stop would look like it was equal to stopper, because it would just check the first 4 letters of stop and see that they're all equal to the first 4 letters of stopper and say, hey, this is great. You weren't sharp enough to send me 2 words that are the same length. That's your problem. I think they're equal, because I've got 4 characters that run between first one and last one, and they look like the same first 4 characters that started at first 2. I think that they're equal. Now, if you go the other way, you say, well, I'm going to compare stopper to stop. it's going to go through the first 6 characters of stopper and trying to compare them to the first 6 characters at first 2. And so if first 2 only goes to stop, then we see how the comparison there goes off the end of that, and you might end up with any number of bad things happening. Your program could crash. You could get undefined behavior, which is generally even worse than crashing. But be aware that this is how standard equal works, and this is the kind of thing that you have to read when you start to read documentation. We say, I want to use this equal function. It looks good. What's the parameter set? Oh, there's 3. Why is there 3 of them? You have to understand what's going on there. So what it does is it returns true if in that range of first one to last one is equal to the range first 2 all the way up to first 2 plus last 1 minus first 1. And this is a half open interval on both of these. So when I say first 1 to last 1, it means starting at first 1 and going up to but not including the one that last 1 is pointing at. So last 1 is pointing just past good data. Or in our standard C string, last 1 would be pointing at the null terminator, because you never want to read the null terminator in terms of value. You can use that to stop, but it's not good data. So the same thing here, we say that the second range, the one that starts at first 2, we know that it starts there, and then it has to go that same number of characters. It's going to return false if they don't match. All right. Here is not exactly the way this is implemented in the STL, but it's a good way to think about how it's done. And you can see something similar to this on C++.com and or cppreference.com. So we've got those 3 parameters coming in, first 1, last 1, and first 2. And we've got this little for loop here that checks. As long as first 1 is not equal to last 1, as long as there's some data to be compared, I'm going to check to see if first 1, dereference first 1 and dereference first 2. If what's there is equal, then I say that it's good. If it's not, then I'm going to return false. And this loops through all of the ones in the first 1 range, and then when we fall out of the for loop, we return true. If somewhere in the range we find a fault, we return false. And that's how standard equal works. So here's a job interview question. Implement a variant of this function that takes a customizable object equals comparator. So this one only works, obviously, because of line 5, for objects that can be equals equals compared. Now, if I don't have that, if I've got my own custom object, maybe I've got a whole range of zombies that I need to figure out which one of these I'm going to shoot before it eats my brains. Well, I want to compare them to see if I've already shot one of them. I might not have already declared my equals equals operator. I might not have overridden the operator equals equals for that object. And if I haven't, I would still like to be able to use standard equal. There's another version of standard equal that takes a 4th parameter, which is a place for a comparator. So see if you can write that. It's a minor change, and hopefully it's not even giving you a bit of a worry. You can just get that written. So here's a nifty example of using standard equal. We've got this function here in lines 5 and 6, really. There's a curly brace at 7. That's called isPalindrome, and we just pass it a string and make one call to standard equal, and it's going to tell us if this word that we've passed it in, or even if the text that we've passed it in, is a palindrome. And a palindrome is a string that reads the same forward and backward, like the word radar, R-A-D-A-R. So if I start at the end, R-A-D-A-R, it looks like if I start at the beginning, R-A-D-A-R, or Bob, B-O-B forward is the same as B-O-B backward. Some other ones that are common are a phrase that's madam, I'm Adam, and that one doesn't really take into account the spaces there, so it just sort of looks at the actual characters, but that's what a palindrome is. And then we've got this, just a little test harness for calling yes or no this string is a palindrome or not, and it calls isPalindrome by taking this equal function. Remember, we needed a place to start and a place to end. That was the input string. And then the thing that we're comparing it to was another place to start. And so those are my 3 parameters. And this is all taken care of with one call to standard equal for checking a palindrome. We start at the beginning of the string, and then we've got the 3rd parameter over there. That's our begin of S. Remember, that is our reverse iterator. And so the reverse begin iterator actually starts at the end of the string, and as we plus plus, it moves toward the beginning. So we've got this reverse iterator as a 3rd parameter coming this way. We've got a forward iterator going this way, and every time I check one of these things, if they're equal, I move in, I move in, I move in, I move in. If I get to the middle, there's one item, and I don't even check that, that's okay, because that's a palindrome. If I've got an even number of characters, I get right next to each other. That's why I can start at begin of S and go all the way to begin of S plus the string size divided by 2. Using integer division there, it's going to make sure that I don't go past the middle. If I've got an odd number, I'll go right up to, but not include that. All right, so down here we've got 2 calls to it. Test radar, of course, is going to give me a true. It's going to print out something that looks like radar is a palindrome. We've got the ternary operator there. It calls is palindrome, gets a bool, passes it to the question mark. If is palindrome returns true, it prints is. If is palindrome returns false, it goes after the colon and prints is not. So that's where we get radar is a palindrome, hello is not a palindrome. All right. Here's a simple job interview question. Again, we're going to keep throwing these at you here. We're getting close to the time where you're ready to fly off on your own, leave the 281 nest, if you will, ride down the street without 281 training wheels, however you want to see this. So we're going to throw some more job interview questions at you. You're shown one fruit at a time, and what I have is the option of these fruits. I've got apples, bananas, pears, and oranges. There's only those 4 types, nothing else. Any fruit that I show you is going to be one of those. And I can stop whenever I've seen the same fruit or the same type of fruit twice. How long does it take, in worst case, for n fruits? Meaning, how many of these do I have to see before I know if I've got a duplicate? I can stop when I detect a repeat. Does this take me linear time? Can I get this done in logarithmic time? Is this something that can be done in constant time? Or is it something else? Be careful on this one. It's actually a really simple one. We start to think about things, we got to be sure we know what we're talking about. So as with any interview question, when you think you've got it, great. Give yourself another breath or 2, double check, and then dive into it. There's so much time that you can save by sort of wasting a little bit at the beginning. I got this, and start writing right away. Or you can say, I got this, take a breath, give it a thought, maybe come up with another example or 2 to confirm that you've got it, and then give the answer. Or then start writing the code that is the answer there. So just some cool tips there. And I see the first answer that's correct out there from Rebecca. That's correct. It is big O constant time. Because even though I've got n fruits, I could have 400 fruits. Since there's only 4 different types, the most I could go is 5 fruits before I saw a duplicate. Orange, apple, pear, banana, orange. Yeah. Orange, you glad I didn't say banana? Sorry, I got kids. All right, that's strings and sequences. We're going to go into this a little bit farther now. And we're going to start looking at lexicographic comparison. Yes, I told you I would say it one more time. So from here on out, though, I'm going to save my tongue. I'm going to call this Lex Compare. Lex Compare is a lot easier than saying the other one. I promise you should try it. So here are the rules of Lex Compare. And this is the one, Lex Compare is how we put dictionaries together. So you already understand Lex Compare. This is just a chance to put all of the rules out in a way that you probably haven't seen them in quite some time, if ever. So the rules are, first we're going to compare each of the ranges one element at a time. So that's important to note that all of these comparisons, even when you use some nifty library function, if I'm trying to compare one string to another, there is not a magic bullet that can get past looking at each one of these ranges one character at a time. So worst case, this is going to be linear. I have to look at every single character in both ranges to make sure that they're equal. So if they're equal, I've got to look at every single character. There's no magic bullet there. If one is a prefix of the other, like like birthday or birthdays, I still have to look at every character. And I get to the end of birthday and I've got more to work on, then I can say, well, that's not exactly going to work there. Or I guess I wouldn't look at birthday and birthdays because they've got different lengths. But if you come up with something else where you've got a word, two words that are the same until they get to the very last character, right? Then there would be one that still have to go through everything character by character, and that's the worst case. And there's nothing special about it. You can make that inner loop as lean and mean as you can, and that's of course what the STL has done for us with our comparisons. But in the end, they're going to be linear because they got to look at all the things. So as we look at each one of these comparators, each one of these sequences, or each one of these ranges, we compare them element by element. I'm looking at everything. The first time I see a mismatch, that defines which range comes before or after the other. And so that's lexicographically less, meaning closer to the front of the dictionary, or lexicographically greater, which is near the end of the dictionary. So the first time I find a mismatch, that's when I know which one should go first or last, right? And you can get something like and ant, A-N-D, A-N-T, and as soon as I see that difference there, A and N are equivalent, and then when I see the D and the T, it tells me, well, the word with the D comes before the word with the T. And if I change that to a longer word like and anteater, I still am going to go A and N and find that the D comes before the T, and so that the and word comes before the anteater word. So that's when I say the first mismatch defines which one goes before the other one. If one range is a prefix of another, that means the entire range is completely found at the beginning of the other range. So I already used the example ant, and then later I extended that to anteater. We can think of ant as being a prefix of anteater. A-N-T is the first three letters of anteater, A-N-T-E-A-T-E-R. So we've got a prefix. So what I do there is I say, well, the shorter one is less than the longer one. The shorter one would come in the dictionary before the longer one. So ant would be found before anteater. That's the rules of Lex Compare. If two ranges have equivalent elements and they're the same length, then they must be lexicographically equal. They're the same length and they have no differentiation there, then they're the same. An empty range is, of course, less than any non-empty range. And that is sort of a generalization here of this prefix rule. I think of ant as followed by the sequence empty versus anteater as ant followed by the sequence eater. I can see why the thing with the less, the empty range is less than a non-empty range. So ant is ant followed by the empty sequence, and anteater is ant followed by the eater sequence, right? So that's why I say that ant should show up before anteater, because ant is followed by this empty range in ant, and ant is followed by a non-empty range in anteater. Two empty ranges are, of course, then lexicographically equal because they've got the same number of elements and they've got no distinctions between them. There you go. So there's the rules of Lex Compare in bullet form. Now in a nice less than list here, I've got something that shows me all of those rules set back up here. I've got the empty string coming before anything non-empty. I've got A coming before AB, so this is a prefix A comes before B. I've also got A coming before B because now they differ, and the first place that they differ shows me which one is less than the other one. Here I've got AB showing up before B because even though B is shorter than AB, the first differentiation comes at the first character, and A shows up before B. And you would expect that, though. You would expect to find happy before I in the dictionary, for instance. BA comes, of course, after B because it has more characters. B is just another prefix. BA followed by BC, that shows the differentiation there. Somewhere off in the middle, not just the first character. And then BC0 there shows how we've got longer strings that give us more things. Overloading comparison operators in C++. One thing that we don't want to do is implement all 6 of them. The STL is one of the things that's written to give us a lot of optimization. It's written there to help us write less code. And so the STL is almost always going to use either less than or is equal to, equals. With those 2 operators, we can do all of the 6 operators that we need because we've always got negation. So if I want to say not equal, I can just write the equals and put a not on the outside of that. And I don't have to write 2 operators. How about if I want to write greater than, but I already have less than written, I don't have to write another function. I just change the order of the parameters. If I'm trying to write A is greater than B, that's the same thing as writing B is less than A. If I've already written less than, I don't have to write greater than. How about less than or equal to? I can do the same thing. I can say, let's change the order of these things, and I can put a not on there. So A being less than or equal to B means A is not greater than B. So if I turn that around and say B is not less than A, that's the same thing as A is less than or equal to B, and so on. So I can get all 6 of these operators just by writing 2 of them and using the negation operator, the not. So all of my comparisons end up using just 1 operator, sometimes with a not there. But we wouldn't want to sort of implement less than or equal to by using less than and equal to, right? You could do that if it's less than and equal to. Less than or equal to, I should say, yeah. Using those 2 with a logical disjunction there would be more work than I needed to do. I'd be calling 2 functions for the price of 1 if I would just turn the operators around and negate. So that's a bad way to do it. If we wrote those 2, that's all we need. How about applied strings? We talk about some common implementation tricks for some class T here. If I write some compare helper, when I'm trying to do this, one of the ways that we compare things is with this less than, equal to, or greater than. When we're talking about things that can be put in sequence, then we need to know whether one comes before the other one. And so we'll write some helper function here that's going to return 0 when they're equal, or negative, some negative value, generally -1, but as long as it's less than 0, we know that x is less than y, or lexicographically less than y. If it's a positive value, 1, for instance, we could say that x is greater than y and should be after y in the dictionary. We write these things, and we can do some really good processing there. Some optimizations for strings. We talked about short strings not needing dynamic memory because the 32-byte object has room for 15 bytes in there. So that's an optimization. And when we first got that new in the G++ compiler, we were already working 281, and all of our projects had to have their timings updated drastically because it made working with strings so much faster. Previously, it was always jumping over to the heap. Even for a 4-byte string, we'd have a pointer that would take you over to the heap, and you'd get back at it, right? Now, these new ones keep everything in-house as long as it's short. In C++, we use, in C, we use null termination, of course. This simplifies my operator less than, because if I'm comparing ABC to ABCD, I don't have to worry about length. When I get to the null terminator of ABC and I'm looking at that next character, as I'm looking at this character time, I see A versus A, B versus B, C versus C, and then I get to the null terminator versus D. And the null terminator has the absolute 0 value, so it will be less than D. So I don't even have to write anything special there. I can still figure out how to pull off prefixes just from operator less than. In C++, strings of a different size are not equal. That's important to note. So rather than even bothering to check this thing character at a time, the first thing that can be done in a constant amount of time is say, are these the same length? Because if they're not equal. And that's a constant time work there. So that's just some optimizations here that we've seen there. Other things that are pretty nice, we talk about vectorized CPU instructions, and this is a situation where we know we're going to be doing things on a regular basis. Working with strings is just a thing that computing does. There is always going to be some string work, some comparisons, some modifications, some things like that. So there are vectorized CPU instructions that allow you to work on multiple registers at a time, and this is great for speeding up string operations. Like I said, that happen quite regularly when we're working, and this is a place where there's actual hardware written to do things that we most commonly do in terms of comparisons and searching and things like that. So this is another way to do some optimization for strings. I mentioned Compare Helper on there's no new line ending character in C++ strings. When you call for the C_stir, right? That's the function that will give you the equivalent character pointer. There is going to be a null terminated thing there. So part of what goes into that is needing a null terminator there. So there is a null terminator that exists there, but not all of the C++ functions need to use it. So for instance, if I was going to do something like check equal with 2 C strings, it wouldn't be worth comparing the lengths to figure out if they were equal first, because you couldn't calculate the length of a string in constant time in a C string. You would have to do a character by character count to figure out, well, this one is shorter than the other one. Well, while I'm doing that character by character count, why not just do my comparison? So there is a null terminator in the C++ string. It's just only used when absolutely necessary, because we do have these pointers that have the beginning and end of the code. We can use anything that does a sequence operation in the STL or C++ style stuff is just going to do that sequence to sequence thing where we're checking a range, and even though the thing that the end iterator is pointing at is just a null terminator, since that's never read or needed when we know that we're just looking at this iterator at a time, the null terminator actually exists there, but it's not always used by the C++ functions, if that makes that a little clearer. For example, here I've got this compare helper, and this one is going to be just using this less than to look for things. And so when we do run into this null terminator, we'll see how that can speed things up here. So compare helper uses const string reference S0 and const string reference S1. I feel like I want to just go change this slide right now, but I'm gonna leave it. It's not my job right now. Okay, so what we're gonna do is compare helper, and if S0 should come before S1 in the dictionary, we're gonna return -1. If S1 should come before S0 in the dictionary, we're gonna return +1. If S0 and S1 are equal, we're going to return 0. All right, so first off, we're going to start by grabbing a couple of lengths. I've got len0 and len1, and we've stored those into a couple of constant size t's there, and that's probably done just to make my slide fit here, honestly. There's no real need to do this. You don't get a whole lot of speed up there by checking that. We do access that in constant time here. But with a really long string, yeah, I think that's just to make the slide better. So don't worry too much about why we did that const reference, not a reference, but a copy of those lengths in line 2. It's just because it makes that min here not take up so much horizontal space so that it doesn't have to wrap on the slide. So now I've got a for loop that says I starts at 0 and I want to count to the minimum number of characters in these strings, right? So I don't want to walk off the end of the short string because I'm reading the long string. So my for loop only goes up to the length of the shortest string, and then of course I ++I it. So as I look at this, I'm going to be looking for the first time something is not the same here. So I've got if s sub 0 at I is less than s sub 1 at I, I'm going to return a -1 because that's that thing we saw from Lex Compare. The first time I see a distinction between the two strings, I know right away which one comes first, and it's the one that's less at that point. So here I'm able to say if S0 is less than S1, I'm going to return -1. However, if I go the other direction, if S1 is greater than if S1 is less than S1, if S1 is less than S0, then I'm going to return a +1. So this is where I'm finding a distinction here in the for loop. The for loop is going to travel as long as they're the same. As soon as they're not the same, or I've reached the end of one or both of the strings, the for loop is going to be exited, right? I'll exit it as soon as they're not the same from inside, or when one of them or both of them terminates, the for loop will end and I'll pop out here. So I can then say, if I've come out of the for loop without exiting the function, without using one of these return -1 or return +1 statements, I still may return -1 or +1, but that's because one of the strings is longer than the other one. And that's what these two checks here in 9 and 11 say. If len of 0 is less than len of 1, then I'm going to return a -1. So we have to check this after we've checked all the common characters, because I don't want to say, well, the shorter string is always better, right? Because that always comes earlier in the dictionary, because that would give me a word like zebra coming before avalanche, right? Just because zebra is shorter. So I have to check for the common characters first, and then if there's characters that remain, then the one with the remaining characters shows up after, the one with the fewer characters shows up before. That's what my return -1 in 10 and return +1 in 12 are. However, if I've gone through the entire for loop and there's no differences and the lengths are the same, then I can return 0. All right? And this entire function was written in a way that does the thing that is least likely to happen. It doesn't test for that. And the least likely that you will find two characters that are equal. You're much more likely to find two characters that are not equal. Why? Because there's so many characters, even in the English language. If we're just talking about the lowercase letters, if I choose one character, there's 26 other characters that could show up in the next, on the other side, that I could be trying to match it up with. And more often than not, that's either going to be a less than or a greater than, and we test that, rather than say, well, if this is equal to, most likely it's not. Well, if we've got that test that says, well, if it's equal, return 0. Well, we did that, and they weren't equal, then we would still have to do, well, is this less than, or is this greater than? And so that's why this one is written that way. This is three-way string compare. As I do a runtime analysis on it, of course, I can look through all the characters if I needed to in the worst case. So this big old linear, and I can do this in a constant amount of space because I'm just needing to keep track of indices / pointers or whatever you're going to actually implement this with. You can't get any better than that, right? You can't get better than a linear case time and constant extra space, because you do, in the worst case, have to look at all the characters. And if you can get away with a constant amount of extra space, then you can't do it cheaper than constant. In average case, however, this is a lot better than worst case. For random strings, like I said, if I take any two words off of this slide and I try to compare them, chances are they're not the same. And moreover, chances are that I know that right away, really quickly, only a first character or two into it. So picking the third word on the second line and the fifth word on the eighth line, right? So third word on the second line is better, and fifth word on the eighth line, 1, 2, 3, 4, 5, 6, 7, 8. All right, well, there's only 2 words there, but we'll say that the second one is versuchen, however you pronounce that in the German. Versuchen versus better. If I was to compare those 2 words, I can say right at B versus V, they're not the same. I don't have to look through all of those characters. Most of the time, average case, I need to check a couple of them. How many words on this slide actually have more than 2 characters in common at the beginning of the word that are not the same word? There's not that many, right? I don't know if there are any. I see compare and complexity. There we go. Line 3 has got complexity, and the last line has compare. Now, as I go to compare this, I'm getting to that on average case / worst case linear time here. I go through C-O-M-P before I come to my first difference, A for compare and L for complexity, right? And at this point, I've already covered 5 of the 8 characters in compare, or 5 of the 7 characters in compare. So that's on the order of linear time, but every other word set on this page is going to be done in 1 or 2 characters because random is nowhere near dictionary in the dictionary. So runtime analysis, we find that average case goes really fast for random strings. How about Lex Compare in the STL? Of course it's there, and you can pronounce it for yourself. You can even go look it up for yourself, which I strongly recommend. This here is a screenshot of one version of this at cppreference.com. Might have been updated since this time, but only slightly. You can also find this at c++.com. We see a few of the different ways that you can actually call this function. Now, Lex Compare uses the 2 iterator version for both ranges, right? Because Lex Compare is going to be able to tell us whether or not and comes before Andre in the dictionary. It'll also tell us whether anteater comes before ant in the dictionary. So I don't have to worry about there's always got to be enough room in the second one. I'm going to send full ranges here. First one to last one, first 2 to last 2. And then I can compare the entire range and figure out which one of these ends up before the other one in the dictionary. We've got execution policies, which we haven't really talked about in 281, so we'll skip that one for now. The 2 that are really important are really just the first one and the third one. And we look at the hints down at the bottom. Says the first one, elements are always compared using operator less than. So whatever I'm giving it in this range between first one and last one, or first 2 and last 2, those things have to be comparable with less than if I use this version here. If I want to pass in my own comparator, then I end up using this third format, which is just adding a 5th parameter, which then takes a binary predicate that takes 1 item from the first one, last one range, and then 1 item from the first 2, last 2 range, and compares them, returning true if the one from the first range should come before the one in the last range. And that way, I can do a Lex Compare with anything. I can Lex Compare stock orders or Lex Compare planets, however you're working on your data set. All right. Here's one way that Lex Compare could be implemented. Just like we mentioned before, this is the type of thing that uses STL style iterators. And we've got this coming in with a couple of forward iterator types, right? That's what our template line at 1 here. 2 different forward iterator types, and why there's 2 different types of forward iterators is it allows us to compare sequences in different containers, right? I can have a couple of vector iterators for first one and last one, and a couple of deck iterators for first 2, last 2, and they wouldn't have to be the same. If I only said there was forward iterator type, then I would have to have one function that could only handle things coming from the same type of container. I have to write one for this container, I have to write another one for a different type, so they simplify that just by saying we're going to give you two separate iterator types so that they can be used. As long as they work like forward iterators, I can dereference them to be read from, I can compare them, and I can increment them. Those are the things that I need out of a forward iterator. Lex Compare would then work. So this is Lex Compare work, and we see that as long as first one does not equal last one, and first two does not equal last two. So this is the point where we say, I'm going to make sure I don't run off the end of either one of these two ranges. So this loop is going to be going as long as there's something in common in terms of length for the two strings. If I ever have a situation where something in the first range is not equal to and is less than the thing in the second range, I return true because the first range comes before the second range. If the thing in the first range is greater than the thing in the second range, and all we had to do here was just flip the order of those things and use the same less than operator. So now we say if dereference first 2 is less than dereference first 1, return false. That means that the thing in the second stream is less than the thing in the first stream. It should definitely then come after it. So we would say false. They're not in the right order. At the end of this, I've just got a nifty little comma operator there that allows me to do both first 1 and first 2 on the same line. That's all it does. It saved us some vertical space on the slide. If you want to understand about how the comma operator works, it does all of the things comma separated and then returns the value of the last one. So since we don't actually store the return value of plus first 2, no one cares. We can just use a comma operator here and put these two things on the same line and save some vertical space. Now, if you wanted to do that on your 281 final exam, you could do it. It would not be unfair. You've seen it here. Understand it. Don't mess it up, but understand it. You also get to use a comma operator in for loops if you've done that when you wanted multiple increments in the increment step, or maybe even multiple declarations in declaration step. Those are other places you can use a comma operator. But all it does is it just does both of those two things separately and returns the value of the last one. In this case, since we're not keeping it, we don't care. But it does increment both of our first 1 and first 2 pointers. When I say pointers, I mean iterators, obviously. They're forward iterators. Finally, if I get out of the while loop without having exited the function, without using one of these two returns as my out, if I get out of there, then I will end up having to say, well, the shorter one should still show up as the first one in the Lex graphical compare, the first one in the dictionary. And this tricky little line of first 1 equals last 1 and first 2 does not equal last 2 allows me to return true or false properly. So I get out of here. That's because the prefixes are the same. Then if first 1 equals last 1, the first one is empty. So that means it's the shorter string, so I should return true. If it's not empty, right, I say first 1 equals last 1. No, it doesn't, because it's first 2 that is equal last 2. That's the shorter one. On the other side, I've got first 2 does not equal last 2, which we know to be false. So that would be a false and whatever. We end up returning false there. So this version of it gives me the proper true or false after I get out of the while loop, comparing characters where I know that there's characters in both sequences. Here's an example of using Lex Compare. I won't dwell on this. It's just some great code here. So what do we got? We've got something that does print characters, and we use this to print characters out of a vector and using some string separator, right? And that separator is how I get from separate string to separate string here. What this does, if you look at it, we've got a for each there. This is a nice piece of work there. For each, which is an STL sequence function, and it's going to process this sequence. And then we're using a lambda here, and so everything in the sequence, it's going to send to cout space separated. So here with this one for each loop, we've printed everything in this vector of characters, one character at a time, space separated, and then at the end we print this separator, which is something that's passed in. So that's my print character helper function. The rest of this code here, we'll see something we haven't talked about a whole lot, but there's a Mersenne twister, this MT19937. MT19937, the M stands for Mersenne, the T stands for twister. It's a type of random, a pseudo-random algorithm, right? It's something that we know that if you're running a standard compliant MT19937 Mersenne twister and I'm running some on another compiler on another piece of hardware, it doesn't matter. If we start with the same seed and then generate 10,000 random numbers, we'll still be looking at the exact same random number on the two devices. So that's what this is really doing here. And so if that's something that's interesting to you or even confusing to you, you should go look it up a little bit. It all comes out of this random include here. That's where we get MT19937, as well as the random device comes out of there as well. But what this does is it takes some vector of characters, not a string, but kind of like a string. It's got these A, B, C, D characters, and then I've got a copy of that here in V1 and V2. What I'm going to do is kind of shuffle these things with this function shuffle from random that takes a range and shuffles those things. So it takes the range from begin of V1 to end of V1, and then it uses my random device here, which is my Mersenne twister, to do that. So that's the shuffle function. And what this does is it keeps doing a Lex compare as I'm looking for something to find the situation where I've got one in the V1 being less than the one in V2. As long as the one in V1 is not less than the one in V2, it keeps printing and shuffling, print and shuffle, print and shuffle, print and shuffle. So that's how Lex compare works. This is an example to play around with it. All right, an application here, removing duplicates. Given I've got a container of string objects, what I need is to leave only one copy of each string. So I have multiple copies of each string possibly present, and I am running low on power. I'm gonna have to go get a power supply. Stand by. No, not that. All right, we're back here. Sorry about that. Where I am, there's multiple laptops and singular power cord. Life on the run. Yeah. All right. How about removing duplicates? So first what we want to do is just sort. If I can sort the given strings, you use standard sort from the STL. You can use operator less than. The duplicates now are going to be next to each other. Now all I need to do is compare the neighboring strings with operator equals, and I can get the answer out of that. As long as I copy only the first of the duplicate strings, I can use standard unique from there, and then I can do this. So try working your way through that one. Got some blueprint to it, but it's a good problem solving sort of thing to pull off. All right, searching and string fingerprints. I got to go fast here. We got a few more slides to go, but this last important topic is something that is good to understand, and they may very well be on your final exam. So make sure you understand this. I mentioned earlier talking about finding a needle in a haystack, and I remembered hearing this expression as I was growing up, and it wasn't until I started teaching 281 and I ran across this slide when the real feeling of what it must be like to try to search for a needle in a haystack actually hit me. I remember I looked at this slide and it gave me a panic attack, and I don't usually get that panicky, but I just looked at that poor guy sitting there on the ground trying to find a needle in this gigantic pile of hay, and it really brought home what finding a needle in a haystack must be like. All right, string find. This is the public member function of the C++ STL string object. So this find gives us some other string that we can search for, and there's a few different ways we can do it. We can call it with another string, We can call it with a character pointer. We can call it with just a character, right? And we're looking for that thing that's being passed in inside of the current string because we're calling this as a member function. We've also got the option to pass in a place to start if you want, a place to start on the current string. So this is useful as you're trying to find the next or all of the versions in one. You might say, well, find it and remember where we found it. Now I'm going to call find again with a second parameter being, well, where I found the last one, let's start after that and move forward. So that's what that is used there. We've also got this third version of it where we might be only looking for some limited number of characters, maybe not the whole thing in the number of characters because I've passed in this character pointer. I only want to find some prefix of things that are equal. So that's what this one is talking about, string find. And how might this be done? Brute force way to do it is just use this two nested loops, which we call a sliding window. So what I'm doing is I'm taking something that I'm searching for. I think of the thing that I'm searching for as obviously being shorter than the thing that I'm searching in. So in that case, I don't need to look at the entire string that I'm searching. I only need to look at a portion of that string that I'm searching that is as long as what I'm searching for. And so you sort of think of that as being some blinders. I only need to see these 4 characters, and I've got this sliding window. I can slide over some characters, I slide over, and I only look at 4 characters at a time. That's all that's necessary. And that's where the two nested loops are. The outer loop, which is the one that goes from the beginning of the long string all the way to the end of the long string. And then the inner loop goes from the beginning of the short string to the end of the short string. And I say, well, if these 4 characters match, in the example here, I've got a search string that looks like I'm looking for A, B, C, A. So I only need to look at 4 characters of the big string. And if they match, then I've found it. If I haven't found a match, then I just need to move over 1 spot in the big string and start over again. How does this work, this brute force algorithm? This brute force algorithm says I'm going to be looking worst case at length of the needle times length of the haystack. Why is that? Because for every position in the big string, I might look at every character of the small string. Now that's not going to be common. This is great because it's worst case. For instance, I might find something like that when I'm searching for A, in this string that's got A, B. Because every time I get through those first 5 A's, I get a match. And then when I go to find the B that follows what I'm looking for, and I find another A, I say, well, nope, that's not it. Let's move over 1 space in the big string. Let's slide my window over. Now I'm looking at the next 6 characters of the big string, and they go A, and then there's another A, and it doesn't match. So I slide my window over 1 more character. Now I'm at the 3rd character in the outer string, in the long string, and I go A, and then I find another A, and so I slide my window again. So worst case, I'm going to look through every character of the needle for every position of the haystack, and that's big O of length of needle times length of haystack. The average case, though, just like we said earlier, most often strings don't match. That's just a thing that has to do with the way random occurrences occur. Usually things are not the same. So in the average case, as I check the first character, say, oh, they're not the same, and I move to the next character. So as I'm checking the first character of the needle, if it doesn't match the current character of the haystack, then I just slide over 1 in the haystack. So in the example here, I'm looking for A, B, C, A, and as I start on the haystack, I've got A, B, C, D, and then I find that they don't match. But as I slide my window over, now I'm looking at the second 4 characters of the haystack. I'm looking at B, C, D space, and right away up on my first comparison, B, C, D space versus A, B, C, A, I know after 1 character that doesn't match. So I can move over another one. Now I'm looking at C, D space A, which doesn't match A, B, C, A right away. And then I move over to D, space AB and compare that to ABCA, and that doesn't match one character in. So most of the time my inner loop is going to perform some constant number of iterations. It's going to check 1 or 2, maybe 3 characters, compare versus complexity, maybe 4 or 5 characters, but most of my characters are going to be a difference there. So on the average case, this brute force string search really only ends up to be about big O of length of the haystack, which is pretty good. STL implementations usually choose this algorithm because it's easy, it's simple, it's usually fast in practice. However, it does have this worst case length of needle times length of haystack thing. So since worst cases do appear realistically in strings, if you're really doing some string work where this might be the case, you might want to make sure that you've got a proper string searching algorithm implemented, one that's going to be working for your particular application. One way that we can do this is with doing some pre-processing. This is not as fast on most strings, but it does make my worst case time go away, right? It makes my worst case time now be big O of length of needle plus length of haystack. And when you're talking about some things that are decent size, that could be pretty reasonable. So if I got a maybe I'm looking at some 3 billion base pairs in a DNA comparison. I don't want to do some 3 billion times 100,000. I would rather do 3 billion plus 100,000. That's a lot smaller. So I wouldn't want to fall into my worst case scenario. So even if it took me a little bit longer to do my general searching, but it prevented me from ever hitting the worst case, that would probably end up being worth it in a particular application. So it's important to know when that's good to use it. So how is this better than brute force algorithm work? Well, the idea is we want to speed up the inner loop. We know when I've got worst cases that this isn't going to be helpful to me. So what I want to do is perform most of my equal comparisons for strings in a constant amount of time, because that is where I'm going to get my speed up there. So this makes my length of needle, that's my inner loop, is controlled by that. So if I can speed up the inner loop so that my equal comparison gets done in a constant amount of time, then that's what makes my length of needle times length of haystack just look like length of haystack, because I'm multiplying by a constant there. The worst case complexity is similar, but worst case inputs are not as obvious and they're rare in practice. So how do we speed up our equal comparisons? Well, what we're going to do is compute what's known as a string fingerprint. Now, we talked about this when we were talking about hashing strings. We talked about taking a string and converting it into a number. We can then call this number the string fingerprint. It's kind of like the unique identifier for that string. That is not the string, but it's a way to get it. Much like my fingerprint is not me, but if I've committed a crime, my fingerprint is a way to get me. All right. One thing that we know about these string fingerprints, just like when we were hashing, is when the fingerprints are different, then my strings are definitely different. They must be different, right? When we were hashing, we said when our hash ints are different, then our keys are definitely different. But because of the way we resolve collisions and whatnot, when my fingerprints match, then they could be the same, but, they could be different, but usually they match. And so that's what we've got here. When the fingerprints differ, the strings must differ, but when the fingerprints match, the strings rarely differ. So what happens then is, if I've got this comparison that's constantly showing me different fingerprints, I can easily move on. And it's only when I find fingerprints that are exactly the same that I have to actually do the work to make sure that they are different. We don't really worry about what the actual numbers mean. We're not using these for addresses now, like we were using them for addresses in the hash table. But if we keep this number hanging around for a fingerprint, then I can just compare these two integers quickly, right? And so it seems like, well, when is that useful? Well, if I've got 100,000 character string and I've got it fingerprinted, and I've got one sort of 8-byte or 4-byte integer that is the fingerprint for that value, then I take some other 100,000 character string, I just compare their fingerprints, If they're different, I know right away in this 4-byte or 8-byte comparison that these two sets of 100,000 byte pieces of data don't match. So that's pretty powerful there. So there's a bunch of different fingerprinting functions, but we'll be looking at one of them and seeing how that we can use that. So one simple but poor fingerprinting function is to just add up all the character codes. If I take all of their ASCII codes and just add them up, then that's something. I mean, it certainly converts some string into an integer. So for instance, like this fingerprint on Tom Marvolo Riddle versus I Am Lord Voldemort, in that case, well, I'd find that fingerprint is a pretty poor fingerprint, because it would say that they're equal. Or would that actually be wrong? Because I think they are equal. Oh, that's meta. That's meta. Those strings are not the same. All right. So if we had a fingerprint function that had a few collisions, most of them don't show up in practice, we could solve the following problem. Given n strings, find the duplicates by comparing their fingerprints. Remember, when the fingerprints match, we have to check the strings for equality in case the fingerprints matched by luck. But when the fingerprints are different, I don't have to do anything there. Right? I know right away that the fingerprints are different, the strings must be different. We can sort the fingerprints to find duplicates and all kind of cool stuff there. So that's what the use of fingerprints can do for us. So we'll look now at one particular fingerprint. We saw the adding the ASCIIs up. That wasn't so great. Now I'm going to be looking at the Rabin fingerprint. So here, instead of adding up character codes, I'm going to view them like decimal numbers. So this is the same way that I know that 321 is not the same as 123. They both have the same digits in them, a 1, a 2, and a 3. But the ordering of them and the placement of those values tells me a different thing. So the 3 in the hundreds place contributes more to the number than the 3 in the ones place. So I'll take the ASCII codes of these characters. TOM space M are 84, 79, 77, 32, and 77 again. And then I'll start to build this running fingerprint, which is just like how I build numbers. So I build 321 by taking 3. Then I multiply that by 10 and add 2. That gives me 32. Then I multiply that by 10. That gives me 320. And add 1, which gives me 321. I'm going to do the same thing with these characters. I'm going to take T, the first character, and multiply by 10. And then add the second character. Take that quantity, multiply by 10 again, add the third character. Take that quantity, multiply by 10 again, add the fourth character, and so on. And this is going to be a way to give me a fingerprint. This is going to be a way to make my string turn into an integer. And we've only used 10 here because we start with our base 10 that humans are so happy to count in. Right? So that's why. It just for illustration purposes, to make it more understandable, like 321, like 123, we're going to use this TOM times 10. Normally you would use something larger than 10. We want to make sure that we don't have an overlap here. So I don't want two numbers to be confused because I haven't multiplied by something large enough. All right? So what this does, though, in the bold at the bottom here says shuffling the characters usually changes the result. And you can see why here. By the time I get to Tom space, I've multiplied 84 by 10 4 times. And I've only multiplied 77 by 10 once. So now if I change the order of that and I multiply 77 by 10, it certainly contributes, if I multiply 77 by 10 4 times, it certainly contributes a different amount than if I multiply the 84 by 10 just once. And so that's why shuffling the characters changes the result here. So with my sliding Rabin fingerprint now, we're going to do something similar to our sliding window brute force search, but rather than sliding window brute forcing it, looking at every possible character in the window, now I'm just going to calculate a fingerprint for my first window, for the first M characters, and M is going to be the length of the string that I'm searching for. So I calculate the fingerprint of that first set of characters in the haystack, and I calculate the fingerprint for that needle. I can compare those two fingerprints in a constant amount of time and say, well, they're not the same. Then what I'm looking at is not what I'm looking for. That doesn't sound like a whole lot of improvement, and in fact, it's not. Right there. But When I want to slide my window now, this is just a simple mathematical operation. I have to say, I'm going to take out the influence of the first character and add the influence of the fifth character. So if I'm talking about a window of size 4, if I remove the influence of the first character and add the influence of the fifth character, now I've got a new window. And I can do that in a constant amount of time, no matter how long my window is. My window is 100 characters. Removing one character at the beginning and adding one character at the end is a constant amount of time. My window is 6 characters. Removing one at the beginning and adding one at the end is the same constant amount of time. So sliding my window now takes a constant amount of time. And if, as is normal, there is a set of strings that are not equal, sliding that thing over in a constant amount of time and comparing it to the search strings fingerprint also takes a constant amount of time. And so I can keep sliding this over and sliding it over and sliding it over and then checking in a constant amount of time and sliding in a constant amount of time. And now I've got this new comparison. So now my total work here is looking like something like a big O of M, which is the width of the needle, the number of things I had to do that no matter what to measure the needle. And then I only had to do a fingerprint for every starting character in the haystack. So I do big O of M work plus big O of N work. And now I've got big O of N plus M as opposed to big O of N times N, which is big O of length of needle plus big O of length of haystack instead of big O of length of needle times big O of length of haystack. So that's the Rabin fingerprint. Now we can apply the Rabin fingerprint to the Rabin carp string search in the way that I just described here, right? We take the fingerprint of the needle, which I can do in linear time, and I can check to see if the haystack starts with the needle, which is by taking the window, which is the prefix of the haystack, that's the length of the needle, and if the fingerprint of the window is not equal to the fingerprint of the needle, then I know that they're different, because remember, if the fingerprints are different, the strings must be different. If the fingerprint of the window is equal to the fingerprint of the needle, then it might be the same. Right? So if I jump here to, sorry, I said that backwards, right? If the fingerprint of the window does not equal the fingerprint of the needle, then I jump to 3, right? And that's when I slide the window over by removing one character on the left and adding one character on the right of my haystack fingerprint. If they are equal, I jump down here, right? Right, I guess I'm skipping ahead, right? So I said if they're not equal, then I can jump to step 3. But if they are equal, I need to check to see if the actual strings are the same. Because remember, I can have a fingerprint of the window and fingerprint of the needle equal to each other, but not actually be equal, because there is a chance that there's a slight chance that there is a miss there. So then I do need to check the actual string there, and that's where I may need to do some work. Most often, we're not going to do that very often. So it's not going to add a whole lot to it. So here we go. If more characters remain in the haystack, then I can just repeat here. This is me just sliding the window, right? That's what my loop does here, and this works. This is the Rabin carp string search. All right, I'm over time here. How do we get past this? We talked about these long strings, and we're constantly multiplying by some value. It's only going to work if I don't overflow. So for long strings, every time I'm performing these addition or multiplication operations, I'm going to end up with overflows. So the easy way to do that is just use modular arithmetic. So every time I add, instead of just adding, I'm going to add and mod by some prime. Every time I multiply, instead of just multiplying, I'm going to multiply and then mod by some prime. The graphic over there shows how we look at 11 o'clock plus 4 hours. We think of that as 3 o'clock. That's what mod has done for me. It's gone from 11 o'clock to noon and then 3 hours past that. One of the reasons they use military time, which is 24-hour time, to clarify that. But the way that this modular arithmetic works is x plus y becomes x plus y mod prime, or x times y becomes x times y mod prime. So what happens then is my conventional arithmetic rules carry over. I can say that x plus y is equal to y plus x before I was doing modular arithmetic, and it's also the same after my modular arithmetic. So I can do the things like x times y equals y times x. I've got this distribution. x times y plus z is the same as x times y plus x times z. All of those things are the same, but I protected myself from overflow. So now I can calculate this fingerprint, and that's also one of the reasons why we can show up with multiple strings that are different having the same fingerprint. Because of this modular arithmetic, we can have some combinations there that carry over. So I mentioned here the time complexity, of course, is when I have different substrings and they never produce equal fingerprints, the runtime is just big O of length of haystack. Every time I've got a collision, like we talked about collisions and hashing, when I've got the fingerprints are the same, then I have to spend the length of the needle time to check that the needle is actually equal to that window in the haystack. But if it's not, then I can move on. So because in practice collisions are very rare, they don't usually compare to meaningful pairs of strings, then I end up with not a lot of those collisions. And the larger my prime numbers are, the more infrequent my collisions are going to be. And what we're going to do here is choose, instead of 10, I kept saying we're not going to use 10 because 10 is just a way for us to understand it. We use 10, we'll use something like 2 to the k. Why is this? Because I can do this faster in hardware. When I multiply by some power of 2, instead of having to do actual multiplication, that operation can be optimized by the compiler to do what's known as a bit shift, which doesn't, it just slides numbers over. The 1010's combination, it slides it over here. So we don't have to do any addition. It goes a lot faster there. So when we look at the implementation here, we'll see that this base that's used is line 2 here. I've got something that base is equal to 128. So that's what I'm multiplying by. Every time I add a character, I'm going to multiply by 128. So this version of it goes through and finds the length of the needle. That's n. Length of the haystack, that's h. Then we've got some factor that we're going to multiply by. As I build up this fingerprint, I'm going to take the first character, then I multiply it by the base and add the second. Then I multiply that by the base and add the third. Then I multiply that by the base and add the fourth, and so on. So when I've got a string that's got 5 characters long, say I'm looking for that, then I'm going to have sometime, one of those characters is going to be multiplied by that base 4 times to get to that 5th position. So that's what I've calculated here, this z. And so what I'm going to use is that z factor to divide out the first character that I'm removing so that I can add a new character in the end. So I want to calculate this ahead of time so that I can use it over and over again. In this first 4 loops here, line 6 through 9, we calculate little n and little h, which are, of course, the needle fingerprint, which is going to stay the same throughout. And then the h is the current window fingerprint, which starts at the beginning of the haystack. And this for loop here from 10 to 19 goes through sliding that H window through the haystack. And every time I look to say, well, if the needle fingerprint and the haystack fingerprint are the same, then let's double check to make sure that they're the same with an additional for loop. If they're not the same, then I just keep going. I break out of this for loop, which breaks me out of here. If they are the same, then I can return I, and that tells me that I have found the place where the needle can be found in the haystack. If not, I'm just going to keep sliding the window as long as I can without going out of bounds while I is less than h minus n, because I only need to slide it over until the window is just wide enough to stay in the haystack. And then I do this quick little thing here, which is the constant time work to change the old window fingerprint to the new window fingerprint. What we're going to do here is we're going to take off the first character and add the last character, right? So we needed that z up here that we calculated in 4, and we're going to take that first character and subtract it from the haystack, and then we're going to add the next new character, always modding by prime when we do this work so that we don't run off of our data type. So that is the Rabin carp search, and if we don't end up finding the string, of course, in the haystack, then we return -1 at the end. All right, that was searching and string fingerprints. That's going to put us at lunchtime. I am happy to talk with you. We'll see you in office hours this afternoon.